Heaps are a specialized tree-based data structure that satisfy the heap property, making them particularly useful for efficiently managing priority-based tasks, implementing priority queues, and performing sorting algorithms like heap sort. Unlike binary search trees, heaps do not maintain a strict ordering between sibling nodes. Instead, they maintain a partial order that allows fast access to the minimum or maximum element depending on the heap type. The two most common types of heaps are the max heap and the min heap. In a max heap, every parent node is greater than or equal to its children, ensuring that the largest element is always at the root. Conversely, in a minute heap, every parent node is less than or equal to its children, which guarantees that the smallest element is at the root. This fundamental property makes heaps ideal for implementing priority queues, where quick access to the highest or lowest priority element is essential. Heaps are generally implemented as complete binary trees, meaning that all levels of the tree are fully filled except possibly for the last level, which is filled from left to right. This complete structure allows heaps to be efficiently stored in arrays, with parent and child relationships easily determined using index arithmetic. For a node at index I, its left child is located at index 2i plus 1, its right child at index 2i plus 2, and its parent at index floor I1, 2. This array-based representation avoids the overhead of pointers used in linked structures and enables efficient memory usage. Additionally, because heaps are complete binary trees, the height of a heap containing n elements is O log n, ensuring that key operations such as insertion, deletion, and heapification maintain logarithmic time complexity. Insertion in a heap begins by placing the new element at the next available position in the array, which corresponds to maintaining the complete tree property. Once the element is inserted, the heap property may be violated if the new element is greater in a max heap, or smaller in a minute heap, than its parent. To restore the heap property, the newly inserted element is repeatedly swapped with its parent in a process called heapify up or bubble up until the correct position is found. This ensures that the root still contains the maximum or minimum element as required. Heap insertion is efficient, with a worst-case time complexity of O log n, since the height of the heap determines the number of swaps needed to restore the heap property. Deletion in a heap, particularly the deletion of the root element, is slightly more complex due to the need to maintain both the heap and complete tree properties. The root element, which contains the maximum or minimum value, is removed, and the last element in the heap is moved to the root position. This replacement may violate the heap property, so a heapify down or bubble down process is applied. In this process, the new root element is repeatedly swapped with the larger child in a max heap or the smaller child in a minute heap until the heap property is restored. Like insertion, deletion is also an O log n operation because it traverses the height of the heap. These two operations, heap insertion and deletion, form the core of the heap's efficiency, making it a suitable choice for applications like priority queues, task scheduling, and event-driven simulation systems. Heaps also support several additional operations. Peek, for instance, allows quick access to the maximum or minimum element without removal, which is an O1 operation. Build heap is an operation that transforms an arbitrary array into a heap and can be accomplished in O(n) time using a bottom-up heapification approach. This is particularly useful in heap sort, where an unsorted array is first converted into a heap, and then the maximum or minimum element is repeatedly removed and placed at the end of the array to produce a sorted list. Heap sort leverages the heap's properties to achieve O(n) log n sorting time. providing an efficient alternative to other comparison-based sorting algorithms. There are also specialized heaps such as d-ary heaps, which generalize binary heaps by allowing each node to have d children. These heaps reduce the height of the tree and can improve performance for certain applications, particularly those involving high-frequency priority queue operations. Fibonacci heaps are another advanced variation that supports more efficient amortized operations for decrease key and merge operations, making them useful in graph algorithms like Dijkstra's shortest path and Prim's minimum spanning tree algorithms. These variations highlight the adaptability of the heap data structure to different computational requirements. The advantages of heaps include their ability to efficiently maintain a dynamically changing dataset in priority order, their suitability for both memory and disk-based storage due to the array representation, and the logarithmic time complexity for insertion and deletion operations. Unlike balanced binary search trees, heaps do not require complex rotations or balancing operations, simplifying implementation while providing performance guarantees for priority access. Heaps are widely used in operating systems for task scheduling, in network algorithms for managing packet priorities, in simulation systems for event handling, and in database systems for external sorting of large datasets. In conclusion, heaps are a fundamental data structure for efficient priority management and sorting. Max heaps and min heaps provide a clear mechanism for accessing the largest or smallest element in O(1) time, while insertion and deletion maintain the heap property with O log n complexity. The complete binary tree representation enables array-based storage, ensuring memory efficiency and facilitating fast index-based operations. With extensions like d-ary heaps and Fibonacci heaps, heaps offer flexibility for diverse applications, from graph algorithms to real-time systems. By supporting operations such as heapification, peak, insertion, deletion, and heap sort, heaps provide a robust, high-performance framework for managing dynamically changing datasets and are a cornerstone of both theoretical computer science and practical software development. Their simplicity, efficiency, and adaptability make them indispensable tools for any programmer or computer scientist working with prioritized data or performance-critical applications.